Hello everyone, I'm Yufei Chen from Xi'an Jiaotong University and the City University of Hong Kong. Today, I'm going to share with you our work, Teacher Model Fingerprinting Attacks Against Transfer Learning. This is a joint work with Chao, Shen, Wang, and Zhang. So let's get started. Deep learning has shown us incredibly impressive power in the past few years. We now have self-driving cars, we have very good voice assistants, we have powerful language translators, and so on. All of these are only possible because of a high-quality deep learning model. Usually, a good deep learning model is really expensive. First, as we know, a good model relies on a large dataset. Second, we need sufficient computing resources to support the model training. For instance, training a GPT-3 model would cost more than 300 years on high-performance GPU. Sometimes we need to hire an expert team to design, develop, and deploy the deep learning model. So it's hard to build and use a high-quality model when we only have limited training data and training resources. We need to find some way to tackle the above challenges. Nowadays, we have an affordable solution called transfer learning. To train a high-quality model, you can grab a set of layers from a large model trained by others like Google. In the case I show here, the pre-trained layers can help to extract features, and we just need to train several fully connected layers. The model we borrowed from the large company is called the teacher model, and the model we finally get is called a student model. Or if we want the student model to fit better on our dataset, we can also fine-tune the pre-trained layers. This is the most commonly used solution we have so far. Large companies like Google, Microsoft, and Meta are open sourcing their models to the public so that everyone can build their own student models on top of these high-quality teacher models. After obtaining the deep learning model by transfer learning, the service provider will consume the student model with an API. Through the API, the customer can upload samples and get the corresponding model predictions. In this case, the student model works in a black box fashion. So why bother to hide the student model from the users? Indeed, on one hand, as we spoke before, a high-quality deep learning model is expensive. It is indeed a kind of intellectual property and should be well protected. On the other hand, it is out of the security concern. Once the student model is leaked, an attacker could find out the weaknesses of the model and exploit them for profit or fun. For instance, the famous adversarial example attacks. But is this design safe enough? Unfortunately, we find that as most part of the student model comes from other resources, usually public databases, an attacker can efficiently identify the teacher model. It works like this. After querying the deep learning services several times, the attacker can identify the source of the teacher model. Then he can download the teacher model from the specific model database. As a result, most part of the black box gets exposed. Such attack not only violates the intellectual property of the victim company, but also enables further attack. Okay, so in the remaining of the talk, I will introduce how our attack actually works. At the beginning, let's talk about the threat model. First, we assume that the attacker doesn't know the student model architecture. Also, we assume the target black box only returns top 1 classification result, which gives the minimal piece of information. But we assume the attacker has obtained teacher model candidates from public sources, for example, deep learning frameworks like PyTorch or websites like ModelZoo. Neither the teacher dataset nor the student dataset is available. However, the attacker can collect public datasets like MNIST, CISPA to help perform the attack. The attacker has 2 primary goals. One is to infer the teacher model accurately, while the other is to use as few queries as possible to limit the attack cost. Here is how our attack, the teacher fingerprinting attack, works. First, the attacker selects a normal sample from a public dataset. We call it a probing input. Then, on a given teacher model, the attacker tries to generate a synthetic input, which leads to a similar latent representation with the probing input. As the two inputs have similar latent features, hopefully they will cause the same top 1 classification result, for example, airplane in this figure. Then we send the two inputs to the victim. If the student model comes from the same teacher model, the two inputs will produce the same latent features, and therefore the same classification results. We call this pair of inputs as a fingerprinting pair. We can send a bunch of fingerprinting pairs to the student model. Intuitively, the more matched results we get, the more likely that the student model comes from the teacher model. So, the first step is to construct the fingerprinting pairs. The key of generating the synthetic input is to solve this constraint optimization problem. We can convert it into an unconstrained one by variable substitution, which can be solved with a gradient descent optimizer. You may have seen this technique in many adversarial example papers. We repeat this step for each candidate teacher model and then send the fingerprinting pairs to the target model. The next step is to infer the teacher model. The rule is quite straightforward. For each candidate teacher model, we calculate the proportions of matched responses. Then, we choose the candidate with the largest matching proportion as our inference result. You can simply regard the matching proportion as a confidence score. Here is an example. This row vector represents Wang attack. Among the candidates, VGG19 has the highest score, but in practice, there are chances that the actual teacher model is out of the candidate set, so we preset a threshold. If the highest score is higher than the threshold, we return the inference result. Otherwise, we return null. That means no matched teacher model found. Due to time limit, here I introduce some representative results. In our basic evaluation, we generate 100 fingerprinting pairs for each teacher model candidate. We construct many student models across different transfer learning tasks, different teacher models, and different student model architectures. Here are the basic results. Our attack has correctly identified all the student models transferred by non-teacher models. For 18 student models transferred from unknown sources, our attack returns null for 13 out of them. For 36 models trained without transfer learning, our attack returns null for 31 out of them. This plot shows how the number of queries affects our attack. Here, we define query budget, the number of fingerprinting pairs used for each teacher model candidate. When the query budget reaches 50, the total inference accuracy achieves 100%. It means that we find an efficient approach to steal most parts of a transfer learning model with much fewer queries. But does the high matching proportion always mean a high inference confidence? Suppose the following case, a black box always returns label 1. Of course, we will always get 100% matching proportion, no matter what queries we send. We refer this to the false matching problem. To solve the false matching problem, we propose a more robust attack. We first define the supporting set. For all the matched responses, we remove the most frequently matched elements. The remaining elements compose the supporting set. Then, we have the following statement. We think the inference result is valid only when the size of the supporting set is no less than this lower bound. We observe that when the query number is not sufficiently large, most inference results are indeed invalid. Or, in other words, our original attack is not robust with too few queries. Our attack can also help downstream attacks. Here, we show how our attack helps to mount model stealing attacks. The idea is straightforward. The attacker sends a set of samples to the target and receives the corresponding responses, the labels. In this way, the attacker can obtain a labeled dataset. Then, based on the inferred teacher model, the attacker trains the surrogate model. Okay. So this figure compares the model stealing performance with the different teacher models. In general, when the attack starts with the teacher model used by the victim, it can achieve the best performance, both in terms of accuracy and fidelity. So at the end, I would like to give two feasible countermeasures. First, we can distort inputs by inserting small random noise or perform image transformations like image cropping and resizing. It can destroy the patterns in synthetic inputs. Second, we can use the method called injecting neural distances to make the student model's feature map different from the teacher models. It requires to modify the pre-trained weight, which may introduce extra training costs. Okay, here is the conclusion. First, we propose a simple and efficient attack to infer the teacher model used by transfer learning. Second, our attack can effectively identify the teacher model. And our attack can help perform further advanced attacks. Okay, that's all about my presentation. Thank you.